Hello, and welcome back to AIM Research. This event is hosted by the Center for Academic Innovation and aims to act as a center for conversation, inspiration, and research to inform educational innovation of all kinds. If you have ideas for people that we should invite to come speak at one of these, please do send them my way. This will be a monthly speaker series going forward, and I encourage you to go register for our December talk, which promises to be excellent, from Monique Harrison at Stanford. You can check out all of Academic Innovation's events at ai.umich.edu/events. Today's presentation will be recorded and posted to our CAI YouTube channel after. We will stop the recording in advance of the Q&A portion so that we can have a far-ranging and free conversation. Feel free to submit questions for Zach using the Zoom Q&A function. I'm so excited to welcome Dr. Zachary Pardos today. To share a little bit about Zach's background, he is an associate professor of education at UC Berkeley, studying adaptive learning and AI. His current research focuses on knowledge representation and recommender system approaches to increasing upward mobility in post-secondary education using behavioral and semantic data. He earned his PhD in computer science at Worcester Polytechnic Institute with a dissertation on computational models of cognitive mastery. Funded by a National Science Foundation fellowship, he spent extensive time with K-12 educators and students working to integrate educational technology into the curriculum as a formative assessment tool. After completing his PhD in 2012, he spent 1 year as a postdoc at MIT and is now the director of computational approaches to human learning research lab, teaches in the data science undergraduate program, and is an affiliated faculty in cognitive science. Zach, welcome, and I turn it over to you.
Thank you. So pleased to be here. Thank you for the invite. All right. Okay. So today I'll be talking about the topic of articulation, why it's an important topic, why it's a really difficult task, and my lab's research on AI methods for improving the tractability of conducting this task. I look forward to a robust conversation afterwards. So what is course-to-course? What is articulation? What is course-to-course articulation? Course-to-course articulation is the question of which course, if any, at institution A is academically equivalent to a course at institution B. So you may have courses at institution A being a community college, a two-year school, and which courses there would be considered academically equivalent to a course at institution B. This is an important question for transfer students. Taking courses at institution A that satisfies degree credit at institution B is often required for students to qualify for transfer. But this is a difficult problem. Essentially aligning a two-year program at a different school from the four-year program so that when you transfer, you don't have to take 3 years or 4 years at the four-year program, you can take 2. So these 2+2 transfer pathways are critical for transfer students, for equity, starting at a 2-year and being able to climb up to the labor market opportunities that are afforded to you with a bachelor's degree is an important part of higher education systems. But there's a lot of work that goes into making this work or trying to make it work. This is what the situation looks like in the California system. So we have a flow diagram from the Articulation Policies and Procedures Handbook. So it typically happens for course-to-course articulation, and there are other types, whole program articulation and so forth. We're focused on course-to-course in this presentation, is that the community college will identify a course that it offers that is not yet articulated at a receiving institution, so a four-year school, and they will communicate with the campus articulation officer at the four-year school, say, we think this course is eligible for transfer to your Calculus 3 course, for example. Then there's a series of departmental or faculty reviews where the faculty member will be contacted and asked if they can approve the articulation. Sometimes there's a negotiation that goes on, or more information is requested. Maybe a syllabus is requested, or the textbook that's being used, et cetera. And then if this process is successful, it ends with an official course articulation being entered into a web system in California called the Assist system. So I suppose it's on the internet, but it's the database for California higher education articulation. But there's some issues with this process. It's highly based on demand. So community colleges that are in the physical region of a four-year school get more articulations made between them. And it's a very porous system, meaning there's a lot of missing articulations. 94% of credit is lost when transferring to a private, as estimated by the US Government Accountability Office in 2017. And they also estimate that 42% is lost when transferring public to public. Some of that is because students change their major in the two-year program, and so not everything transfers into the major they've changed to in the four-year, but some of it is also just due to lack of articulation that perhaps should be there. This is also a very slow process, takes a year often for this to complete, and it's open to biases on both ends. You know, you can imagine a bias on the four-year school end, where an instructor may be surprised to hear that a sending school that doesn't have a research program in a particular area is offering a course. They may have questions about if it's a computer science course, what language is it taught in? And it's really a sort of data-starved situation that the instructor is in. They don't know the counterfactual of how well the student will succeed if they're giving credit for that and they don't take their course. So it's a difficult situation. There's also biases potentially on the sending school's end. Right? Community colleges often like to advertise themselves as being good platforms to jump to a four-year institution. So they may be overeager to articulate to courses that might not set students up for success. So the combinatorics of articulation really lay out how difficult this problem is at scale. So if we only consider the 116 two-year California community colleges, I say only, it's one of the biggest community college systems in the nation, but it's only one. There are 23 state universities, which are also four-year programs, and then 9 University of California campuses, Berkeley being among them. So only considering articulations between one community college, which I'll call CC, and one UC campus. And let's say we don't have department to department mappings. So this is the worst case scenario where we have to consider the potential connection of every course at the community college to every course at the UC. That's 63 million pairs, assuming about 1,000 courses offered at the community college and 7,000 offered at the UC. So let's consider the non-worst case scenario. Let's say you do some work and you manually map departments. Sometimes it's not so simple because not all departments are called the same thing. One school may call computer science, another is electrical engineering and computer science, another is information sciences, informatics. And while they're not all the same thing, there could be a lot of overlap. So let's say you did that mapping. And so now you're only considering courses within computer science, for example, mapped to other courses in computer science at the destination school or receiving school. That's still 35,000 links to consider between one community college and one UC. So now if we think about all the community colleges to all the UCs, that's 36 million pairs. And that's not considering the 23 CSUs, that's not considering private institutions, and that's certainly not considering state-to-state articulations. Add to this the fact that every year there's a slight drift in the concepts covered in a course, and there's always new courses being introduced. So the upkeep of these articulations also is a scalability problem. So what do we propose? A data assistive machine learning approach to use institutional data. In the case that I'll be showing you, it's course catalog descriptions and historic enrollments in order to triage this articulation problem and automatically surface candidates for articulation. So I'm saying data assistive and candidates because in this work, we are not proposing that this suggestion system will take the place of faculty engagement, but it can augment it. And the impact of this, where I should say the impact of a scalable approach to articulation is more articulations, which would mean greater credit mobility. Students have more ways to qualify for transfer, greater equity, more opportunities for those who haven't had it in the past to earn that 4-year degree. And it's been estimated that among the students who do transfer, 20% more would obtain the 4-year degree instead of stopping out if no credit was lost at transfer. Wasted credit during transfer is also a huge problem for financial aid. You get financial aid at the 2-year school, you transfer to a 4-year, and let's say you have to do 3 years, or in worst case, or not worst case, but in the non-ideal case, 3 years, that's still a year of financial aid that is not being utilized towards the degree. And these approaches could potentially be generalized to other credit acknowledgement scenarios. For example, giving course credit for military training experience or different experiences and attained in K-12. So the novel data set that was used for a pilot of this study was UC Berkeley data and a nearby community college called Laney Community College in Oakland, which is a 2-year school. And you see the difference in enrollment records. Berkeley had nearly 5 million in records between 2008 and 2016. Laney around 300,000. And then you see the difference in number of students, number of courses. These were the two institutions I used for those reference numbers of 7,000 and 1,000. And you can see there's a big difference in number of courses. So you wouldn't expect necessarily that there's going to be 100% overlap. Certainly, Laney might be a subset of Berkeley courses, but they also may teach things that Berkeley doesn't. And there's a difference in the course description lengths. Berkeley has description lengths of 325 words on average, whereas Laney it's 27 words on average. And you see both have some outlier courses that are only 10 words in the catalog description, which you can imagine could pose a problem for automatic pairing. And then we had 65 articulation pairs between these two schools. And so these are from the assist system. So these are gold standard faculty approved existing articulations between these two institutions. And those articulations from the assist system look something like this, where you'll have the, UC1 course on the left, and then the community college course that credit is accepted from. In the case of the second course, you'll see that you need to take 2 community college courses to satisfy credit for 1 UC course. And then the last example is where there's a UC1 course that is required for degree credit, and it's a lower division course. It's not a junior or senior level course that doesn't yet have a community college articulation. So the idea of this algorithm is that it could be used to fill in that no course articulated cell if there is a candidate out there. So again, the task is a course at Berkeley, academically equivalent to, say, this one at Laney. And it could go the other way too. You could have a course at Laney Community College and you want to know if it's, obviously it's a bi-directional kind of relationship, but you could ask for recommendations for either in the method I'm going to show. You could say, here's a Laney course, give me the top 10 Berkeley courses that are similar to it. Or you could say, here's a Berkeley course, give me the top 10 Laney courses that are similar to it. And it's really a matter of which institution should initiate the articulation request. And while it usually goes from community college to 4-year, I think the system would benefit from it going both ways, with both types of institutions initiating the request. So we're gonna validate the models that I'm about to tell you about on those 65 articulated pairs, seeing if we can predict those pairs, those ground truth pairs. And then later on, are we going to be able to use this model to suggest courses that are unarticulated? So the methods that we proposed utilize both the catalog description and enrollment data. And I'll start with the catalog description, which is more intuitive. So you have the Berkeley title and description of a particular course, and you can represent that as a bag of words, pretty simple, CS61A, and you see its column vector, which is just a 1 if the word is in the description and a 0 if it's not. And the length of this vector would be the total unique vocabulary of all catalog descriptions between the two institutions. You can run TF-IDF, make it only slightly more sophisticated, such that you more heavily weight words that are distinctive and are less common across all courses. So you may want to not consider the word course as an indication of similarity. Instead, maybe programming or AI should be more heavily weighted. And then we use something called description vector, which is just using an off-the-shelf Wordtovec pre-trained model and then averaging all the word vectors of the words in the description. And we just call that description vector. And there have been other incarnations of that in the past. Right, and so once you have all of these vectors, you can run cosine similarity, right? You can calculate cosine similarity of a course at Berkeley and ask whichever of these natural language models you choose, what are the most cosine similar courses at Laney, or vice versa. So Wordtovec is used for that description vector approach. And what is it? It's a way of making meaning from a large corpus of text. Its claim to fame is learning lexical relations between words in an unsupervised fashion, meaning those relationships like capital and country are not given to it beforehand, but it is able to learn embeddings or a semantic space that encodes geometrically these kinds of relationships. So skipgram is the more formal name of the model that we used. And in past work in NLP and AI, it's shown that features of words could be learned, that a word is a capital or that a word is a country, or analogical relationships between different words. So Microsoft is to Ballmer as Google is to Yahoo. That's not right. As IBM is to McNeely is right, as Apple is to Jobs, was right during the time in which the corpus was collected, which is Google News for this 2013 study. And so this is the canonical manipulation that can be done once a Wordtovec model is used. King minus man plus woman equals, and then the model says queen. And so it was able to learn this feature of royalty among king and queen and gender. And we see how a typical Wordtovec model is trained. So that would be utilizing catalog description. That's our approach to utilizing catalog description. But if we stop there, there's a lot being left on the table in terms of data. There's 4.8 million student enrollments of sequential data. So what can be learned from those? All right, this is an example of the enrollment data. It's one sequence. It has CS61B, which is that data structures course. So can we learn something about CS61B from all of these enrollment sequences that it occurs in? And so this question is, the way features of words were learned from a large corpus, can features of courses be learned from a large sequence of course enrollments? So instead of sequences of words, sequences of course enrollments. And the answer is yes, that there's an extraordinary amount of semantic information conveyed by student course selections. And in a number of studies in this +1 article, we chronicle or explicate the ways in which signal is encoded in enrollment data alone. But that's a separate talk. Suffice it to say, we applied skipgrams to enrollment sequences such that we're spanning all the enrollments serialized by just randomizing within semester or within term order of courses, and then treating it as a sequence, and then learning embeddings of courses in this way. So now we have a vector for each course that's only from the enrollments that we can also calculate cosine similarity from. And then it's it's reasonable to think that the catalog description might contain complementary information to the enrollment data. For example, a course rarely says that it's an easy course in the catalog description, but you may be able to infer that it's a relatively easy course, or that students think so, from enrollment patterns. And so that would be a feature of the course that perhaps could be learned from Wordtovec, and then combined with what the instructor, how the instructor describes the course, could lead to a better representation of the course used to calculate similarity across institutions. So a little bit of a detail is, if you have neural embeddings, which is what these skip-gram learned vectors are, for one university and for another, they're not going to be directly comparable because they're in two different spaces. So the common way to link these spaces so that you can then compare elements in one space to the other is to do a translation. And this is how early approaches, early meaning 2013, approach word-to-word translation in language. They learned a linear mapping between one space and another using a handful of known translations, so known word-to-word translations, and that aligns the two spaces so that you could translate to out of sample words. Out of sample as in words for which you didn't know the ground truth translations of. And what you see in this t-SNE dimensionality reduction of each space is there is some similarity in the adjacencies of departments, right? And this is a good sign for this approach being successful, because these same kind of adjacencies were found in language. So zoomed in on a language model, you have 4, 5, 3, 1, 2 in this kind of constellation. This is a PCA dimensionality reduction. And then looking at an embedding of Spanish that was trained completely separate from English, you see a similar geometric pattern or constellation to the Spanish equivalent of those words. And that's why, and that similarity geometrically is what allows for this alignment or linear alignment to work, is that even for languages that have a completely different syntax like Chinese, they still exhibit a lot of these isomorphisms. Okay, so for the evaluation, again, 65 articulation pairs, we're going to do a leave one out cross-validation, where the model knows about 64 articulations. And then for the 65th, we give it the Berkeley course and we ask it to make recommendations of the top Laney courses that might satisfy the that might be academically equivalent. And so we know which course we're expecting because it's an officially articulated course. And we look to see how far down the list of recommendations that officially articulated course is. And that's how we score the model. Details of these results can be found in this paper published in ACM's Learning at Scale. So beginning with the simple catalog description bag of words model, the y-axis is recall performance. So that's the accuracy. And the x-axis is the number of courses that are recommended. So recall at 5 means that algorithm is allowed to show 5 examples, or it's allowed to predict 5 courses. And recall performance means out of the 65 instances, what percentage of those had the correct course recommended in the top 5? So the more recommendations you give the model, the more likely it is that the correct expected course falls within that top N. Okay, so at 5, we start with a little above a 60% accuracy. TF-IDF, which makes more salient distinctive words over more common words, improves a little bit at all endpoints. And then application of pre-trained Google Wordtovec, where we're averaging the Wordtovec vectors for each catalog description, doesn't do as well as the basic approaches with only 5 suggestions, but then improves with more suggestions. And then the approach that only uses enrollment histories to infer similarity between courses gets 50%. So below the catalog description approaches, but still finding some signal at 50%. Remember, the number of Laney courses is 1,000. So it's still a non-trivial task to surface the right course in the top 5 out of 1,000 possible courses. But combining catalog description with enrollment data based representations is better across the board, and quite substantially so, above 70% accuracy, which says that there seems to be some complementary information in these two sources of data about a course. And if we look at some statistics of the course, different model results, median rank is how far down you have to go to find the right result. Wordtovec plus, that should say DeskVec, is 2. So it's the second result, that's the median rank. And then you also see the standard deviation of the rank. And with Bag of Words, you can imagine why there's such outliers, because of the number of courses that have less than 10 words used to describe the course. So in simpler terms, some catalog descriptions are really bad and they are awful sources for trying to estimate the similarity between courses. But if you incorporate enrollment data, it's hard for enrollment data to be bad unless there's a very small amount of enrollments in a course, right? But otherwise, it's a solid complementary source of information. And if we do PCA on the course embeddings, like Mikolov and colleagues did on word embeddings, we see for UC1 and CC1, again, a similar constellation. The Java course is in about the same position relative to the other computer science courses than the C++ course. And then data structures, that one's a little harder to place. It's not exactly isomorphic with its pair. And so that could be an example of where it commits an error, where the best course is not in the top suggestions. And so now it's time to, that was a validation. So it's trying to predict existing articulations, but the aspiration of this approach is to recommend articulations that don't exist yet. So among the 185 unarticulated lower division UC1 courses, we had to ask ourselves which was the most promising to generate CC1 candidates from, right? We don't expect that all 185 have appropriate community college mappings. And so we had to come up with a heuristic to choose which will be the most promising 185. And I ask you to look at the paper for the details of how we decided on the most promising. It's also the case that the articulation officers only have so much bandwidth. So it wouldn't be practically workable for us to deliver 185 spreadsheets of recommendations to them. Better that we deliver, maybe 5 to 10 at first. So here you see the UC1 course, and then the algorithmically suggested top articulations or courses with the highest academic equivalency as inferred by the model for this 3D modeling course, and then for Introduction to Economics. And you see sometimes it does some weird stuff. At the bottom, it suggests jazz, which I'm comfortable saying isn't academically equivalent. So some challenges. Let's see here. All right. Some challenges. Wordtovec, the enrollment-based approach is not available without enrollment data. It should be obvious. Which the important part is enrollment data is harder to get than catalog description. Current machine translation methods do require existing articulations. So using what I've shown here, you wouldn't be able to articulate between two systems that don't have any articulations between them. And the accuracy, at 70% with 5 recommendations isn't enough to just say this could do it automatically, right? It needs human validation, not just because the policy at institutions require it, but it wouldn't be a good idea to let it go on by itself. And there's open research questions on how to effectively incorporate faculty engagement. And this is the policy challenge. So there's both computational methodological data science challenges and institutional policy challenges. But we did show that enrollment data is complementary to catalog description for estimating similarity between courses. and that this data assistive approach can at least narrow down articulation candidates the way search engines narrow down results for a query. You wouldn't want to operate and navigate the internet without a search engine. And similarly, I hope we find ourselves in a world where we wouldn't want to operate without some kind of evidence-based and data assistive approach to articulation. Future directions include exploring translation methods for the Wordtovec approach that don't require existing pairs, so that we could translate and suggest articulations between these systems that never have had articulations between them. There are definitely approaches that are promising to do that, just as there are approaches in natural language to translating without existing word-to-word translations available. And then another direction is to develop an articulation network platform with articulation suggestions that are both student-facing, researcher-facing. I know there's some research groups, Kate included, at Michigan that are interested in this question, have been pursuing it from different angles, and a platform that is usable by these different stakeholders could help stir the pot, right, of articulation. Just some notes about, again, on the methodological side, but I know there's kind of equal attention that needs to be paid on the policy side for this to work. But methodologically, these course embeddings are useful for a number of different downstream tasks, from predicting on-time graduation, to inferring prerequisite relationships between courses, to suggesting courses within an institution that are serendipitous, that try to get the student out of their departmental bubble, right? Especially at a liberal arts university, or any university with a broad range of offerings that's interested in well-rounded students. This kind of recommendation could be of use. And while we borrowed many methodologies from natural language processing to do this work, some of the work involved in coming from course articulation and higher education inspired research questions in NLP, which we've subsequently published on at a couple NLP venues. Thank you so much for your attention. Look forward to questions.